So why? From a Bayesian perspective, we can understand as it like every moment we could just see just one aspect of this roof, and we need to fill in the details from the other aspect, but we don't have them. So we use the prior beliefs, the prior structures from our experience to integrate this prior into our current experience so as to have an expectation of what this this one look like. But because for this illusion, because it's not a typical object, so our perception or our Bayesian inference in this specific case is mistaken. Tversky and Kahneman, they like the idea of visual illusions, and they call a bunch of biases they found in human cognition as cognitive illusions. For example, you must have heard just one or some of these terms, like Linda de Martella. Okay. Maybe it's still not beyond psychology. Let me just tell you one of them. We don't have time for all of them. Like say the law of small numbers. You guys know what's a law of large numbers? So law of small numbers refer to the human belief that even we only see a few samples from a population, you still believe it's very representative of the population. Like if for example, you encounter some people from a group, and if this person is very arrogant, you may think, oh, this group is arrogant. Something like this. And but did you know that Daniel Kahneman win the 2002 Nobel Prize? You even did not know that? Okay. So Amos Tversky and Daniel Kahneman, they are very influential psychologists to the both psychology and the economy, because their work has shaped the what we think about humans. Like in economy, like before then, like economists will think about humans as rational, like, but Tversky and Kahneman found a series of heuristic biases in human behaviors that make almost all the society believe that humans are not rational. They have many biases that are unbelievable. And a few years ago, Miller and Gelman, they point out that this kind of ideas actually dated back to Laplace 200 years ago. Um, Tversky and Kahneman just kind of reinvent them. And this is the irrational side of human being. And let's look at right side now. It's John Anderson. So in my last lecture, I introduced his categorization theory that human categorization may be framed as a rational or Bayesian inference with a Chinese restaurant process. The basic idea of John Anderson is deeply influenced by Herbert Simon. the bounded rationality. But what differs Anderson from Herbert Simon is Herbert Simon considers people as um, with an agent with limited computational capacity. But the problem he tried to solve are basically problems in the world. And Anderson goes a little bit further, and he thinks about all the cognitive system as kind of adaptive to the world. For example, one of the famous example is the memory. We know we forget things, and we think this is bad. And what Anderson showed in his paper is a very famous paper back to 1990s. It's if we consider we have very limited capacity to remember just a limited set of things, and then what stuff to get and what stuff to maintain would be a decision problem. And actually, humans are not so bad. They are very good of like things we would like to maintain with the things that we are going to use in the future. So don't feel so bad about the stuff you forget. You probably will not need it in the future. So what's the relationship between these two very different approaches, the heuristic biases and the rationality analysis? In Anderson's time, Anderson did not try to start war between the two. So he said, okay, my theory can apply to memory and characterization, and these are kind of cognition concepts, cognition domains that are very different from the traditional decision making. So I'm happy to see, oh, you guys have the biases, and we are having the rational things. But in our era, more and more that is trying to cross the boundary and try to use the rationality analysis or the basic ideas of we have limited cognitive capacity, but we can use this capacity very efficiently to solve problems in the world and to make our perception and cognition function efficiently. Now there are a growing body of work on it, but in today's talk, I will only going to tell you two studies from our own from my own lab. And if you want to find more examples, a good starting point is the reading material I supplied a few days ago. The first one is a study with my student Xiang Juanren and my postdoc advisor Larry Maloney. It's published. As Tversky and Kahneman wrote in their famous paper on prospect theory, it wrote, in decision under risk, humans sometimes fail to optimize expected gain or expected utility. In particular, they distort probability information. We may use P to denote the objective probability and pi p for subjective probability. And if pi p is plotted as a function of p, we would see an inverse S-shaped curve. That is, we overestimate small probabilities and underestimate large probabilities. An inverse S-shaped distortion like this could account for the Allais paradox and many other decision-making phenomena. And this curve may be described using the linear in Lagrange function. So it's simply we transform the P into Lagrange, the log of P over 1 minus P. And if we transform both the P object probability and pi of P the subject probability into Lagrange, then we have a linear function between the two. The linear in Lagrange or LLO has two parameters. The slope gamma. Both of them are easily to interpret. Gamma is a slope. So if gamma equals 1, then we have no probability distortion. The curve would be reduced to the 45-degree line. And if gamma is less than 1, we see the traditional, or what we saw before, the inverted S-shaped curve. And if gamma is greater than 1, then we have the reverse S-shaped curve. That is to underestimate small probability and to overestimate large probabilities. And this is a crossover point P0. It controls the point where the curve crosses the 45-degree line. So with increasing P0, you have a larger and larger pi p. What we found Thanks. What we found in 10 years ago is similar patterns of probability distortion has been observed in a range of studies across perception, memory, and decision making. So here are just a few examples. We have already had the Tversky and Kahneman's probability distortion in decision and risk. And the middle one is from Adnif's 1953 data on judging the relative frequency of English letters. Each dot is for one English letter. And again, you could observe a pattern of overestimate small probability and underestimate large probability. And if we turn them into the Lagrange, then we see a straight line fit them very well. And distortions may change with individuals. It may also change with tasks. Like in the classical decision and the risk, we have the gamma smaller than 1, but when probability information is provided with implicit in someone's motor behavior, then in decision making, subjects look like they are underestimating small probability and overestimating large probability. You have a gamma greater than 1. Our question is, what controls probability distortion in all of these tasks? And why probability distortion at all? We notice that even probability in one task could span an immense dynamic range. For example, in the plot here, the estimated the frequency of the possible causes of death span about like 100,000 scale, like The very big difference. But if we think about perception, then perception may have an even larger difference. As we know, like in vision, the dynamic range our eye could cover can be uh, as large as 10 to the ninth degree. So how does a visual system, or more generally, the perceptual system, solve this kind of problem? It's adaptation. It's like in every time, at every moment, it's not like our eye can see the whole dynamic range, but we will adapt to the environment. And even you have learned nothing about like vision. I know many of them know much about it. So we all have such experience. Like when we enter from a very so in the outdoor, entering a very dark room, then at very beginning you can see nothing, and a few seconds later you can see something, and few minutes later you probably could see much better. So your eye adapting to the range in the current environment. And this is a very famous illusion of the lightness, the I think lightness or luminance. Yeah, like here these are two squares have the same greenness, but if they have a different background, they look very different. So which means your eye adapting to the background information from time to time at a very fast speed. So we are inspired by how the perceptual system works and propose the bounded Lagos or BLO model. So the basic idea is like this. We know the probability scale is from 0 to 1, but if we transform it into Lagos, then it actually goes from minus infinity. Sorry, this should be an infinity symbol to infinity. And given that, if we think about our cognitive system, we probably have a very limited scale to represent it. And here what we shows is we call from the literature we call it Thurstone scale. It's a scale, it's a limited range length and with limited precision. And what we could do is use this very limited um, capacity scale to represent the probability. So here are two examples. So if we represent a very a wider range, then we probably have a lower precision. And instead, if we choose to represent a narrower range, we probably could have a higher precision. So here's trade-off between the two. Either you could choose to represent larger range to keep more portable values in your representation, but you must sacrifice the resolution. There are three assumptions. First, probability is represented in Lagos, and second is unbounded Thurstone scale. And third, we have some compensation for this representational uncertainty. Here are some technical details I may skip. And what we need to know for today's talk probably is what we do is if we choose to represent a specific range, then we will catch the values outside it to the boundary. So we have a representation that goes from delta minus to the delta plus. And we run some experiment to test the BLO. So we think probability distortion in different tasks, they're all the same. So we test two different tasks. The first task was decision making under risk, the DMR. It's very simple. Each trial, the experimenter would ask participants one question. If you were given a choice, which of the following gambles would you prefer? A, 5% to win $50 and 90% to win nothing, or B, to win $5 for sure. And Gonzalez and Wu, 1999, measured the certain equivalent of 165 different lotteries for 10 participants. So certain equivalent means the experimenter will supply the participant a range of sure reward, the sure payoff, and ask participants to choose for which one you would accept the gamble, and for which one you would then maybe it's easier to say for which one you would prefer the sure reward, and for which one you would prefer the gamble instead. So the experimenter could compute a point that the participant have no preference between these two. And this is called the certain equivalent. It's very much like in perception, we may estimate what we call point of subjective equivalence. Like you have two stimuli and you think they have equivalent luminance or equivalent size, something like this. And in the experiment, there were 11 different probabilities, goes from 0.01 to 0.99. And we reanalyzed Gonzalez-Wu's data, and we also tested 75 participants using the same task and design as them. But our experiment also contains another task, the judgment of relative frequency task, the GRF. So the task is to judge the percentage of dots that are black, like this. So on each trial, participants saw a stimulus like this, and they would input a number, say, what's the percentage of this? Or they would on a scale, they would say, what's the percentage? And here is the data versus the model. Data is the dots, and the linear in logarithm model is in blue. The bounded logarithm model, BLO, is in red. And here it just give you some impression that BLO is actually much better than LLO in DMR and also in GRF for each individual participant. Each small panel is one participant. And on the right side plot, we also shows like what average steps look like, what the differences between the two models.
Can you go back to the model again? So I think there's one equation I didn't quite follow.
Yeah.
On the right, this.
Oh. on the right side, it's like this part is, I think I should use the pointers better. Okay. So on this side is a, what range would I represent? And after we represent something or encode something, let me say encode on a scale, then the next problem is to decode it and to read out it. So our basic assumption is even when the experimenter gives exact value of probability to the participant, but when participants read it into their memory, they could not keep everything. They may have a much less precise representation. So this is a very limited representation with limited precision. And here is this part, kind of Bayesian inference, though not exactly. So this one would be the logos that results from this kind of transformations. And this side.
So what is omega p and what is
Sorry. I think I forgot to change some notations here. This one should be very close to this. Yeah, but there is more. There's
you can
yeah. If you like to see the details, maybe you can open the paper. I put it in the reading material, so it's better to read it from there because the slides was not intended to have all the details. And basically, it's like after we have this noisy representation, assume we have noisy representation, and we may compensate for its possible noise. So it's very close to what you do in Q-combination or the usual Bayesian inference. It's like I would combine it with some fixed point, like to say, oh, I think there's a prior there, and then I have some belief the prior. So I give some weight to the prior, and I put less than one weight to my current measure. It's like this. Yeah. And at the very end, we would transform everything back to the probability scale if you are going to do decision and the risk task to combine it with value, or in the judgment task, this one would just report the probability on the scale.
There's another question.
Yes.
And I was wondering what is the essential differences between the PLO and LLO model. It seems to me that both of them make some nonlinear transformation between the stimuli and the representation. So how do we interpret the differences between them in terms of the experimental results?
A key difference is PLO introduces kind of truncation. So LLO is just you transform the probability into logos, and then you have a linear transformation. And the PLO would assume you can't represent the whole scale. So you will truncate it, like to just part of it. And everything outside it would be truncated to the boundary. And we have some future differences here. I think maybe it's easier to, so this is the difference in their definition. I think it will come easier if I just come to this one. Yeah, the factorial model comparison. show more details in 3 dimensions. And another big difference is the LLO has no future future motivation. Why it should be like this? It was used as a tool to capture the data. The data is basically an inverted S-shaped curve or an S-shaped curve. So we like to have some equation to capture this. And with BLO, we were trying to capture so here first we were trying to capture more like more aspects of the data. And secondly, we are going to use it as something that could expand, like you will see very
Thanks.
soon. So we are not to say BLO is the final model. What we are trying to say is the assumptions we made in BLO, they are better than their alternative assumptions. That's the motivation we do model comparison for most of the time. So what we do is it's called a factorial model comparison. It's like BLO could be, so there are 3 assumptions, and with each assumption, we could expand it into a dimension. So for example, we assume that probabilities are represented in logos, and alternatively, it could be linear, or it could also be this is a known functional form in decision-making literature. It's called Prelec function. It's a functional form that's alternative to the linear in logos. And we could assume that, so in bounded logos model, the BLO, we assume bounds. And we could also show, assume we can remove the bounds, or we just set the delta plus and delta minus to infinity. This is a future dimension. It's about how we combine the encoded value with the fixed point to recover the possible to give an estimate. Maybe you can skip this, or so as you can see, LLO would just one special case in this set of 12 models. Like LL is here. It's logos, it's bounds free, and it's assumed that what you compensate is a constant variance. What's different in BLO is it's assumed that the variance of I should say the noise, the variance of noise to compensate, it changes with the probability. So it's quite intuitive. Like if you assume that the probability Gaussian noise on the logos scale, then when we transform back in the probability scale, we would see something like you have a more precise estimation around 0 or 1, but a much worse estimation around 0.5. And just think about the variance of binomial distribution. You can get the idea. So what we found is with all these assumptions, BLO outperformed all the other 11 models for both the DMR and the GRF tasks. And here we show how BLO, what's the performance of BLO, the model family PLO belongs outperforms other model families. Like here is logos outperform prelec and linear. And here is a bounded is better than bound free. And the particular form of variance is better than the constant variance assumption for both DMR and the GRF tasks. So in other words, all our three assumptions are better than alternative assumptions we tested. In our paper, we actually test beyond this kind of model set. So all this model set is within the framework of cumulative prospect theory, and we also tested additional models outside prospect theory, and we found PLO still better than them. And for a PLO, what we define as capacity is the length of the system scales divided by standardization parameter. What we found is these two tasks, this kind of capacity parameter, they correlate with each other. It's not a very large correlation, but still, I think it's something we and other people ever found between different tasks. Usually, they found nothing between different tasks about a probability distortion. But the key question for our current topic is, does probability distortion reflect efficient coding, like what motivated the PLO? And our answer is yes. So what we did is in our study, we fit our model to participant data, so we can estimate their parameters, delta minus and the delta plus. Meanwhile, we could run some simulation to show how about for them to using a different set of delta minus and delta plus. What would change? Whether so, and we found in our simulation is if we change the delta minus and the delta plus and compute the mutual information between the objective probability and their representations, then we found what's the particular delta minus and delta plus participant use is close to maximizing the mutual information transmitted in the task. So here we also make some very straightforward comparison between what if you have no boundary, just say you set delta plus and delta minus just to infinity. We showed that if you have no, so this is the actual, what participant actual do, and this is if we assume they are bound free, then the mutual information transmitted in the task would be 20% lower than the maximum. But actually, in their actual performance, it was lower than 10%. Our further question is, what controls the slope of probability distortion? Is there any way we can have some prediction about it?
But how do you compute the mutual information information here, it's a little bit too technical for the students here. Yeah.
So first, we need to have an estimate of the, so we have a Sasson scale, and we need to estimate the noise, the precision on it. So what we did is we fit participants' data, fit our model, the BLO model to participant data, and based on the final noise parameter we have, we could do some transformation based on what transformation might actually occur in each task. So we have an estimate on the Sasson scale capacity, and then we assume that if it's quite straightforward. So it's like if for each experiment we have a distribution of probability, right? And with this distribution of probabilities, we just transform it to the final estimate, participant final estimate using our model with noise. And we do simulations for like 100,000 times, and we could see like what is finally fall on the estimation, and then we just compute the mutual information between the original distribution and the final distribution in participant estimate. There are some details. If you are interested, you may find it in the supplementary material of the paper. The idea of mutual information is one of the that has used by other authors like Woodford, like Michael Woodford, and also some Gershman work. So for more information, you may read the reading material. If you feel so confused, I assume you folks did not read the reading materials. Did you? Okay, let's continue. So one prediction we have is the probability distortion is the slope of distortion may depend on the range of stimulus. For example, when it's a narrow range, goes from 0.1 to 0.9, instead of a wide range going from 0.01 to 0.99, you would have a larger slope in this case, in the case of this. And we put some data from previous literature, and we found 12 studies for which we could compute this kind of information, like what's their distribution and what's the slope of distortion. So we did find some correlation between this as we predicted. So this is a BLO paper. Did I run out of time? Okay. I hope I still have some time to cover Tianyuan's work. So let me just skip this introduction part, maybe starting from here. So the second work I'm going to tell you is unpublished. It's by Tianyuan, and Tianyuan is a much greater speaker than me, but because it's my responsibility to give this lecture, so I have to do this for him. Okay. As you know, we already have there are many studies that show people could do Bayesian inference, but there are much fewer studies to study like how we learn probability distribution. In many studies, we just assume either, oh, you need a very long training session for this. Like some studies use a training session as long as like 1,000 trials or even 2,000 trials, and then they just throw out this trial, just as if they did not exist. But one difficulty we noted here is learning probability distribution itself is very important inductive inference problem. So what does inductive mean? Inductive means we don't have a unique answer for this. It can have infinite alternative solutions. Let me just explain a little bit. What we observe are samples from the world, and we would like to infer the generated model behind. Even when considering a one-dimensional data set, the generated model could vary in many different dimensions. So how could people solve this induction problem? In general, inductive bias is needed for solving induction problems. It could be called inductive bias, or in the Bayesian literature, it's just prior. So our question is, what inductive biases do people have when they learn an arbitrary probability distribution? For solving inductive problem in general, Occam, Kant, Galileo, Newton, and Einstein, and many great others, they all suggest Occam's razor, also known as the law of parsimony or the simplicity principle. That is, if multiple models fit data equally well, choose the simplest one. As we know, the development of scientific theories follows Occam's razor. It's also widely believed that human cognition also follow Occam's razor. That's why we can only sample from this line, but we not perceive it as more zigzag line curve instead we perceive it as line, because this one is likely to be a simpler explanation than this. But how about our particular problem? The learning of probability distributions? The evidence is mixed. One line of evidence supports Occam's razor, showing that Gaussian distributions, which can be described by only two free parameters, may be easier to learn than multimodal distributions. But there is also evidence against Occam's razor. For example, these two studies use computational modeling to infer the distributions represented in the human brain. And it seems people represent Gaussian distributions as distribution with multiple clusters. This may sound quite counterintuitive, but let's consider the London bombing example. This is a very famous map. Like each dot shows one flying bomb from the German flying bomb to London during the World War II. What do you think the distribution of these bombs form? What? Subway station? You probably see these two clusters. Like many people see these two clusters around the park and the river. However, instead it's random. And it's also at that time, the accuracy of the flying bomb was way too low to form any clusters. So seeing clusters, if you see clusters, it's probably just your illusion. Some of our earlier work is consistent with such illusions, but the evidence is purely model-based. And because modeling human behavior is also an inductive problem. So when we see multimodal representation for Gaussian distributions, we were not so certain whether it's an illusion of our participants during the experiment or it's an illusion of our modeling procedures. So in recent years, we have worked on developing new behavioral tasks and the data analysis method to more directly reveal the possible biases. Here are some of our previous work. Just show we apply spectral analysis to the distribution reconstructed by human beings and show even for a uniform distribution, they perceive as if it has at least two modes. So what I'm going to talk today, you know, is also along this line. It's by Tian Yuan and our collaborator Wen Liang, and Wen Liang attended the C Neuro 2 years ago. I'm not going to talk this task, and I will start with this task, and for modeling. So the task is called the structure density estimation task, where participants saw a sequence of samples described as lava rocks from the invisible volcanoes and were asked to report these volcanoes. Like they were not only to report the locations of these volcanoes, but also how likely, let me say, the weight and the width of each volcano. So let's just see a demo. These are lava stones. And time to draw the invisible volcanoes, the first location. And then you could use a mouse to draw Gaussians to report the weight and the width. Here is a sanity check, simply showing participants could track the mean SD and standard skewness of the distribution in a reasonably well way. These are some example trials. Each colored line here is the reported density from one trial, and the black dashed line below is a true density. And we can see in this example, even the true distribution is Gaussian. Participants draw two or even three clusters. We have run 3 experiments. The first two experiments use visual stimuli as in the demo. And we tested a variety of different unimodal and multimodal distributions. And to include the possibility that our findings are modality specific, in experiment 3, we use numbers as stimuli. Meanwhile, to include the possibility that participants' multimodal biases came from the multimodal distributions they encountered in our experiment. So we only use unimodal distributions in our experiment 3. Let's just first look at number clusters from participants' report. This is experiment 1, the unimodal distribution, bimodal distribution, and the trimodal distribution. And these are histograms for, we can see the highest part is, it ranges from 2 clusters to 3 clusters, even for the unimodal distribution. And results are similar for experiment 2. In experiment 3 with number of stimuli, still participants prefer multiple clusters, but they would report even more clusters. In our experiment, we had used different sample sizes in this experiment, and we find that when sample size increases, the reported cluster number does not count the ground truth, but even increases like this. It goes from the most frequently at 2 to more frequent to at 3. You can see a move to the right side of these curves. And we also find that the reported cluster number does not rely on the range of stimuli. In the number experiment, 2 sets of stimuli were tested on 2 groups of participants. Numbers in the second set were 5 times as large as that in the first set, but the mean number of reported clusters were almost all the same. Our task provides a rich data set, allowing us to assess information far beyond class number. And here's just one example. We quantify the percentage of overlap between adjacent clusters, like this, in participant reports. The 3 panels from top to bottom correspond to 20%, 10%, or the 5% of overlap. And we could see the data looks like it's 5% overlap or even less. In other words, the representation is sparse in space, confirming the model result of our previous study. This means participants are not just using multiple clusters to approximate the true distribution. If so, at least for the Gaussian distribution, their multiple clusters would be very close to each other, but no. So we may use stereotype multimodality to summarize our empirical findings. And this could not be explained by Occam's-Razor. It's also not because the samples participants saw are too few, because the reported class number even increases with sample size instead of converging to the ground truth. So what's the learning process behind that stereotype multimodal representation? So with collaborating with Wen Liang, we have modeled the data of our structured density animation task and show how this kind of structured representation arises from a sample-by-sample learning process. The basic idea is like this. I'm very happy I have give you a lecture on the China recent process. So much of it I could just skip. So the basic idea is at each time it comes one sample, and with more and more samples, you are going to expand your internal model. So here, what we mean by sample-driven model expansion, the model here is not the model used by the experimenter, but means the observer's structural representation. It's the observer's internal model about the world. Because every time it comes a sample, you have two possibilities, either to group it into the old or one of the old cluster, or you create new cluster for it. And every time a new sample comes, you have some probability to create a new cluster or update existing clusters. So how could one decide what to do with a specific sample? So let's take a closer look. Suppose we start with an internal model with two clusters. In this structured representation, each cluster is described by three parameters: the mean, the SD, and the sample number inside this cluster. And when a new sample comes, it has some probability to join cluster 1. And if so, the mean, the SD, and the sample number of cluster 1 will be updated like this. Similarly, if the sample is assigned to cluster 2, then cluster 2 will be updated. And in the case a new cluster is created for the sample, a new set of cluster parameters is added to representation. The probability that the new sample will belong to a specific cluster is determined by Bayesian inference again. That is, the prior probability that a sample joins a specific existing or new cluster times the likelihood is generated by the given cluster. And as we already know, like this part, if you assume each cluster corresponds to a Gaussian distribution, then it's quite obvious we can just use the Gaussian likelihood to decide. It depends on, in other words, it depends on how close the sample is to the class center and how large the SD of the cluster is. And the prior Dirichlet process, or is used for the as a prior for the cluster assignment, or the special case, the CRP, the China recent process. So we already know this part. And it has recently been approved in statistics that Bayesian inference based on the Dirichlet process prior may overestimate the number of latent clusters in the sample. And this kind of overestimation may even increase with sample size. This is a kind of violate our previous expectation. We usually think, oh, Bayesian inference is kind of normative approach, and with Bayesian inference, we could come closer to the ground truth as soon as we have more and more data. Not necessarily with specific prior, this can be violated. And for us, this can partly explain our findings. If we assume humans use a similar prior, then it can explain why with more and more samples, participants could report more and more clusters instead of going to the ground truth. However, the prior used by human cognition, the Dirichlet process can be unrealistic because the number of clusters can keep growing with sample size up to infinity, which can't be afforded by a limited memory system. So what we have considered in our model here is what we call a more economical model expansion. So by assuming that, okay, I still forgot to fix this. I think it's fine. Okay, so by assuming that the concentration parameter alpha would decrease with the number of existing clusters, the total number of clusters is more likely it will grow much slower with the number of samples. It's more likely to satisfy the memory limit. We will call the original model the basic model, and we will call the new model with the economical expansion as the econ model. And the model fitting procedures like this, we have a very, you probably noticed that because participants could report as many or as few clusters on each trial. So on each trial, the dimension of data is not finite, but grow with the number of clusters. And for each cluster, we need 3 parameters to represent it. So we actually have a very high dimensional behavioral report set. And the CRP model also have a very high dimensional nature because you need to make an inference every sample counts. So as time grows, as samples accumulate, you have more and more possibilities. So it's internally high dimension. And we used a very large time of simulations to do the model fitting. So we can exactly fit the high dimensional behavior report using maximum likelihood estimate. And here is just some visualization of model versus data for example trials, like for basic model and equal model, how it look like. And here's the comparison of the basic model and equal model in AIC for individual participants. And the equal model has an exceedant probability about 99% to outperform the basic model. And the right plot shows that a concentration parameter alpha, which controls the prior probability of creating a new cluster, does decay quickly with the number of existing clusters. Some of our data fitting are still in progress, so I could not show you all the results. I hope we could do next time. Like we not only tested 2 models, but I think over 50 models probably. So there are many very many dimensions of possible hypotheses. So we just varied the hypothesis and tested whether on this dimension, which would be the best hypothesis. one interesting feature we find in the fitted model parameters is there's the prior for the standard deviation of each cluster is kind of narrow and strong. Narrow means you start with assume that the SD of the each cluster is just very small. And strong means it's not readily be changed by the samples. Kind of like the thought experiment I gave in my last lecture, like some person or AI kept reporting the mushroom is poisonous. Like so have very strong. So this shows as our simulation shows such parameter values would lead to a minimal overlap between clusters, just as we observed in the human data, like less than 5% of overlap. So just a quick summary, what we have found so far. And in different tasks or modalities, this was for, I omitted one task. So in both our tasks, we find convergent behavior evidence for stereotype multimodal representations of probability distributions. And by developing modeling methods for high dimensional behavioral data from high dimensional latent processes, we find a learning process with economically expanding internal models could explain what humans participants are doing. So any thoughts or questions? If it's about the second study, maybe you can ask Daniel.
Hello. In the CRP process and your eco model, there doesn't seem to be a mechanism for deleting categories. While in our brain, do you think is there such a mechanism?
What kind of categories?
For deleting categories.
Oh, we did not show this. Right, you're quite right. Our model consists of two parts. The first part is inference. So it's during the when the samples come, we assume when participants observe the samples, they are doing the inference. So when they are doing this inference, there were no model component that allows them to delete anything. Wait. So there's one detail I need to reveal. So in the CRP process I introduced last time in the basic lecture, I mentioned that the full Bayesian inference it could do could like reduce the number of clusters because it just reason on the full probabilities. But in our special case, we use a single particle filter algorithm, and it could not do exactly as you said. It could not delete the existing clusters. So the way we fix that is we assume that this kind of deletion may happen in the reporting stage. So when participants they are reading out this kind of reinference and to report it to output it as the shapes as the number of the volcanoes and there's something happening there. They could adjust. There's some way to adjust the number of clusters. Like we will not just leave out, say, throwing out something. It's like we have some merging procedures going on. Like you may decide to merge these two volcanoes into one volcano, like that.
Thank you.
Yeah, there are also some like splitting stuff. going on. So if we found participants reported more clusters, so we have some procedure to do that.
Maybe by introducing a mechanism in the CRP process, we can prevent the coming to infinity. The CRP reporting.
No. It's not a problem of our algorithm. Let me just back to this one. Yeah, I had thought that before, but Tianyuan found the statistical paper showing that. So this one is not with any, well, it might rely on some specific algorithm, but it's algorithm free. It's not a feature of the approximation algorithm, but a feature of the Bayesian inference and the CRP pile itself. Yeah, even with the full Bayesian inference, you could still get the, but it's very interesting. So we are trying to figure out what features in the human data could be explained by the Bayesian inference itself, and what part may rely on the particular approximate algorithms we use. Yeah.
Thank you.
Questions from the Basels? Oh, there's another question here.
I have a quite general question. Do you believe that our brain is doing the exact computation of probability and Bayesian inference? Recall that in the Monty-Hall problem, it seems that the result is not so intuitively can be determined or deduced. If you have to make some high level inference and probability computation to obtain those the answer. So is it possible to is there possible is it possible to have other mechanisms to explain such behaviors? If you assume that our brain is based on probability computation and such distortion may be may be natural if the assumption is not plausible.
Of course. Um, I'm not a big fan of Bayesian inference, frankly speaking. Um, what I mean is I I don't think we do Bayesian inference for everything. For like, I think Bayesian inference has very strong evidence in perception, but not in cognition. But still, there's some possibility that we are doing it. But this does not mean we only do Bayesian inference. Even for the Bayesian inference, I don't think we exactly do as the formula shows. We probably have some approximate algorithms that help us do this. And so in the psychology and the neuroscience literatures, there are two, we may say the Tversky and Kahneman, they represent one party of this, like this debate, like is the heuristic and biases. And there are still other people like I would say Geranzer, but Tversky and Kahneman think they are different. Like, so many people, not every researcher is Bayesian. And there are also a very large group of researchers, like they are focused on how our brain could use heuristic to solve the problem. And actually, even in this kind of bounded rationality side, Herbert Simon is more on the heuristic. So he thinks Anderson is different from his opinion, although Anderson believes that they two do not have much difference. Anderson is more on the Bayesian side, like so it's the kind of difference is kind of subtle. It's like Simon more believes that we are trying to be rational, but we are using some kind of heuristic to achieve this. And Anderson thinks we have we have this kind of computational or storage constraints, but there are still some of the our brain is doing Bayesian inference or not exactly, but towards this side. And I think if for me, I'm a little bit more close to Anderson and I mean the rationality side. And there are a lot of work going on in my lab that we are following this side. One strength of the rationality side is you can use one framework to unify many different things. For example, you could like assume what's the benefit to remember a word, what's the cost to remember a word. You don't need to invent a different heuristic for each different task. So, but in many different situations, I think there are not much difference between like different sides. It's like if we use, I don't think this rationality explanation is kind of mechanism. I think the word is mechanistic. Yeah, like it's more like how we view this kind of problem, how we solve this problem on the computational level.
Physics.
Yeah,
So the question is, are there neural bases for these computations?
I hope we will find more neural bases for this. And this is also, I think, how this field could move on. Like, so now we have a growing body of study about it's called resource rationality, like to understand many different behavioral tasks, like the probability distortion I mentioned earlier, and also why we distort value information, and why we do like temper discounting. Like all of this, we could use a rationality account to explain. But the problem for the field is we have so many models, and each model is different from other models in some subtle way. Sometimes it may be a big difference in their hypothesis, but we don't have as many empirical tests for them, and also we don't have like how this happens in the brain. So I hope we could find like go further on this along this line.
Questions?
But one thing I should say, I should mention is one thing you could check is probably from Paul Glimcher's lab, like because he has his lab including like Conway Lewis work. They have some work on adaptation and on the value adaptation and how this happens in the monkey's brain. Yeah, that would be the closest, the neural basis.
Questions from the Basel side? Yeah.
Yes.
Yeah.
Can you hear me?
Yes, we can hear you.
Hello. This relates to the first part of the talk. So in decisions under risk, there's a lot of research that shows that when the same problem is played repeatedly with feedback, the underlying phenomena of overweighting of rare events, just as one example, reverses. And then you see underweighting of rare events. And a lot of the effects predicted by cumulative prospect theory are in fact reverses. Can your model also capture that effect of feedback and learning, or can you incorporate that?
Yeah,
What do you
sure.
think about it?
Sure. I think when you have feedback or you don't have feedback, it involves very different mechanisms. And actually, there was a paper by Ido Aref in 2010, and he and other people, I think that they have like 10 to 20 authors on that paper because they run a decision making competition. Like they had some data set that okay, any one of you could um submit your model, your decision model to us and see which one works for best. And what they show in that paper is when we have decision making without feedback or the decision, there's a task called decision from sampling. It's like you observe the decision making with feedback and then you decide for one. And they also have the decision making with continuous feedback, just like what we usually have in the neuroscience task, like the multi-arm bandit task. And they found for these different tasks, the human data are the base model for behavioral model for these different tasks are very different. So they are likely in these different tasks, people use very different strategies. So it's like if you have feedback from trial to trial, then I may not need to represent this kind of probability at all. I may just learn from feedback which one is best. Does this answer your question?
Maybe I can just add that there are a few recent papers that address this exact problem, and this is an hypothesis that I think needs to be tested, whether you really need two different models to capture behavior under feedback and under description, or whether one model can fit them all. And there are a few papers that show a lot of evidence in the direction that one model is enough and one model to capture the cognition under decision and the risk. And uncertainty can capture that, but yeah. Thanks.
Thanks.
Any other questions from either side? Well, if not, let's thank Professor Zhang.
Thank you.
So, Stella, we're